So a first order linear difference equation is any equation where the next term in the sequence is A times the last term plus B. So it's first order linear difference equation. The previous video went over some examples in personal finance, and in the previous video, we found the equilibrium of this equation, B over 1 minus A. So in other words, if you started at B over 1 minus A, you would always stay at B over 1 minus A. If I put B over 1 minus A in for the x sub n, the nth term in the sequence, I get out B over 1 minus A as the next term in the sequence. But here I want to solve. And what does that mean? Well, if we wanted the fifth term, okay, so now we need a starting value for this. So we called the starting value x naught, the initial value. We're always thinking about applying this to personal finance. So our initial investment might be the x naught. And then we would get interest multiplied by A and then add a little deposit each year to get out how much money is in our account the next year. But if I wanted to know what's x of 50, as the example I did in the previous video, you'd need to know x of 49. And to get 49, you need to know the 48th term, etc. So you'd need to calculate all of the terms from the x naught all the way up to x sub 50, which can be done with a spreadsheet, but it would be nice to have what we will build in this formula is what I'm calling the solution. But what I mean is I want an x sub n formula that I can just plug in. So a formula where I can just plug in what's the n that I'm interested in, like 50, let's say. What's the A, what's the B, those are the parameters, and what's the x naught that I start with. So that's what I'm interested in building, a formula where I don't need to get the 50th term, I don't need the 48th term, the 49th term, the 47th term, etc. I can just plug in the values and out pops my answer. All right, to build that, to get there, what I'm going to do is a shift in coordinates. So this video won't have a lot of personal finance stuff in it. It'll look really mathy. It'll be a lot of math. And yeah, one of the terms I'm going to use, one of the concepts I'm going to use is a shift in coordinates. So I'm going to call y's. So we have x's. X's are the value in my account, let's say. But y's, I'm going to make that the difference between how much I have and the equilibrium. So the equilibrium, x bar is just a constant, it's just a number. It's b over 1 minus a. So I'm doing a coordinate shift. So if I'm making up my new sequence of numbers are the y's, and I'm getting the y's by just taking the x's and subtracting the equilibrium. So if I was at the equilibrium, then equilibrium minus equilibrium, the y value for that would be 0. If I was above the equilibrium, the y value would be positive. If I was below the equilibrium, the y value would be negative. The y is the y is how far away I am from the equilibrium, above or below. So this also works. So n could be n plus 1. So that's also true. The next term is just the next y value is the next x value minus the equilibrium. All the y values are just that corresponding x value minus the equilibrium. That's my coordinate shift. Of course, I have a formula for this x sub 1 up here, so I'm just going to sub that in. So now I've got the next y value is equal to a times the previous x value plus b minus the equilibrium. But let's take a look at this equation that I have here. If I solve this equation for x sub n, I'm getting x sub n is equal to y sub n plus the equilibrium, right? Essentially, I'm just moving this equilibrium piece over to the other side of that equation. Now, why am I doing that? Well, here I've got an x sub n, so I could take this and in place of that x sub n, I'm just writing it in terms of y. I'm trying to switch everything from x's to y's is really what I'm doing. So x sub n is equal to y sub n plus the equilibrium. So now I've got, let's write this in a new line to see what I've got. I've got the next y is equal to this equation. But let's expand this out. Let's multiply this a across that bracket. That would be a times yn plus a times equilibrium. Now, let's look at this piece here, and you'll see why we did this. A times the equilibrium plus b minus the equilibrium. Well, actually, a times the equilibrium plus b, that highlighted piece is the equilibrium. That's how we find the equilibrium in the first place. We set x sub n equal to the equilibrium, x sub n plus 1 equal to the equilibrium, and solve for this. So this whole bracket, in other words, is 0. If I don't see that, then you could actually sub in b over 1 minus a 4x bar and simplify this bracket, and 0 will result. Long story short, when I do that coordinate shift, this is what I get. The next y value is just a times the last y value. But I need a y naught. I had an x naught. Oh, well, our equation here is y sub n is equal to x sub n minus x bar. So I have a y naught. The initial y value, y naught, is just equal to x naught minus x bar. I mean, all the y's are just that. Their corresponding x value minus x bar. So if I have an x naught, I have a y naught. But let's look at this form of this equation. So I start off at y naught. Y1, the next y value, is just going to be a times y naught. So our sequence is going to go y naught. The next value is just take the last value and multiply by a. So it's going to be a times y naught. The next value is going to be take the last value and multiply by a again. Well, it's a times a. This is going to be a squared times y naught. The next value is multiply by a again, so a cubed times y naught. So I can see the pattern here, right? The nth term is just going to be a to the n times y naught. So I have a solution then. Y sub n, or in the y's anyway, y sub n is just equal to a to the n times y naught. There's my solution for the y in terms of the y. If I want to know what the 50th y term is, I can get it without getting all the other y values. Just a to the power of 50 times the initial y naught. Of course, my original formula were given in x's. So let's just take this y formula and change it back. So in for y of n, I want to change it back to x's. So in place of y of n, I'm going to put this x of n minus x bar. I have a to the n. In place of y naught, I have this x naught minus x bar. Now my formula has only x's in it. Remember what I wanted in originally was I wanted to have x of n being a function of n, a, b, and x naught. And I guess I can have that if I just move this over to the other side as a plus. Yeah, I'm good. I'm done. That's what I want. I've got x of n equal to a formula of a. Oh, you say there's no b. Well, the x bar has a b in it. In place of that, let's write our x bar as the a over 1 minus b. So here's our solution. So now let's write this as a let's put this for summarize this. If I have a first order linear difference equation, I have an x naught value, I have an equilibrium value, then the solution to that is a to the n all times x naught minus the equilibrium value plus the equilibrium value. So this that box is the summary of all the stuff, all the formulas that we've built for anything that satisfies a first order linear difference equation. Now let's think about this for a second. So x naught initial amount. Let me get rid of that. Let's think about that for a second. We saw that we found the equilibrium by solving the difference equation. But what if I started at the equilibrium? In other words, if I set x naught equal to the equilibrium, if I set x naught equal to b over 1 minus a, then this would be b over 1 minus a minus b over 1 minus a. This whole bracket would be 0. And the next term, all the terms, would just be b over 1 minus a. So what does that mean? An equilibrium is the equilibrium. Fine, we knew that. But we can also talk about the stability of the equilibrium. Because we saw examples in the previous video where we went towards the equilibrium, we call that a stable equilibrium, or we went away from the equilibrium, we call that an unstable equilibrium. And now we can kind of see what's governing whether that equilibrium is stable or unstable is the a value. So it's a to the n. So if a was, let's say, a number bigger than 1, 1.05, using the first example from the previous video, then this would be 1.05 to the n, and as n goes off to infinity, 1.05 times 1.05 times 1.05, that shoots off to infinity. And so we're going away from the equilibrium. But if a was a fraction, there was an example in the previous video where a was equal to 0.988, then that would be 0.988 times 0.988 times 0.988 to infinity. That would go to 0. If a is a fraction, this piece goes to 0 as n goes to infinity. So then 0 times that whole bracket, that disappears, and eventually a to the n becomes the equilibrium of a over 1 minus a, b over 1 minus a, b over 1 minus a. I flip those upside down. That was supposed to be the equilibrium. B over 1 minus a. All right, now we're good. So what am I saying with the limit? If I take the limit as n goes to infinity of x sub n, well, it equals the equilibrium if a is a fraction. So if a is a fraction, because a fraction raised to infinity would be 0 and this would disappear, become 0. But if a is not a fraction, then this piece goes to infinity, maybe minus infinity, depending on the signs of a and b and x naught and that kind of thing. But our equilibrium is stable Our equilibrium is stable if the A is a fraction. It could be a negative fraction. Negative fraction maybe doesn't, the A doesn't make sense with in a financial example, but just in general, it does make sense. In the math, it makes sense. And otherwise, it's an unstable equilibrium. If A is not a fraction, so if the magnitude of A is bigger than 1, then x of n just goes to infinity, plus or minus infinity. So I'm going to write this by, well, you know what? I'm just going to call it an unstable equilibrium. So you go shooting away from that equilibrium. But here's where the meat of what we did, the most important pieces of what we did, exist in that highlighted box. So in other videos now, I'm going to just straight use this, the math we built, to solve some more personal finance questions.